Hi, this is a video about the covalent bond. This is lesson 1, module 2. So we've been talking about ionic, but now we're going to switch over to covalent bonds. And remember, a chemical bond is just kind of a mutual attraction that two atoms have for one another. And there's really just ionic and covalent bonds. There's also metallic, but we're not really going to cover that. So stability-wise, the reason why things bond is to become more stable, lower in energy. So the compound that's formed is going to have less energy and be more stable than the elements separate were. So if you remember, ionic bonds are between metals and nonmetals, and that's the transfer of electrons. Covalent now is going to be where they're sharing their valence electrons, and by doing that, they're still going to be able to acquire that stable octet of electrons. So the other thing is that once you form the covalent bond, you form molecules, and molecules are different than ionic. So if you remember, ionics are really just cation, anion, cation, anion over and over in a crystal lattice. Molecules are just each their own. So for example, like here's methane. We're going to learn how to do these Lewis structures later. So it's its own thing. It's not packed together with others. So here could be another methane, but they're each individual molecules. So a molecule is what you get when you have a covalent bond. So we do have these diatomic molecules. These are always gonna, if they don't bond with something else, they'll bond with one of themselves. So these are something you just need to know. The rest of the class, the rest of the semester. And sometimes just to remember these, I say this kind of silly way of remembering, which is Brinkelhoff. It's just all of these elements together, and then if you just remember they're diatomic. So on the periodic table, it's really, they make a 7, where this would be the halogens, and this would be oxygen and nitrogen, and then hydrogen way over here. So you can remember them however you want, but it's something that you want to know. And the reason they're diatomic is because they're more stable to be together bonded than to be alone. So here's an example of diatomic fluorine. In order to be stable, the two fluorines will share a pair of electrons. You can see. So then each fluorine is able to essentially count those electrons towards its own octet. So this fluorine over here has 8 valence electrons. And then similarly, this fluorine over here also. So they can both count those shared electrons towards their octet. So we're going to talk about single covalent bonds. So single covalent bonds, this is what I showed you with that methane earlier, but it is when they're only sharing one electron. So the way that we would do it is we would show the fluorine, there's your single. So a line is the single covalent bond, and it represents 2 electrons. And then the other non-bonding electrons are still there, but they're not part of the bond. So this is called a Lewis structure, and we're going to learn more about how to draw these in the next lesson. Sigma bond, we're not really going to spend too much time. I just want you to know that a single covalent bond is also called a sigma bond. So there's also double and triple bonds, and double bonds is where they're going to be sharing 2 pair of electrons between 2 atoms. So for example, oxygen will double bond and look like this. So the double bond, 2 lines, kind of looks like an equal. That is really 4 electrons because each line is 2. Triple bonds, example, they're sharing 6 electrons, so nitrogen does this. So that is the triple, and that would be equal to 6 total electrons. So bond length and strength. The shorter, when you have a multiple bond like that, that bond length is going to be shorter than this double, and then that would be shorter than if we just had a single bond. So the more bonding, the shorter the distance between the elements, the more tightly held together they are. So as bond length goes down, so when you go from a single bond to a double, a little shorter, to a triple, the strength increases. So this is the strongest. So therefore, then when you talk about bond energy, the energy that would be needed to break the bond, this one would, the shorter they are, the more energy it takes to break it apart, which really means ultimately the more stable it is. And you can see here, this is just a table really showing those same elements I was just talking about, and the bond length is getting shorter. If you look at, just ignore the 10 to the, and look at, it's getting smaller, but the bond energy to break the bond is getting larger as you go down from the single to the double to the triple. Endo and exo, we've been somewhat talking about this. If we were going to break those bonds, it is endothermic. There's energy that would have to go into what we call the system, which would be the chemical that you're trying to break the bond of. Exothermic means it's going to release energy. This is what, if you remember the demonstration where I formed the magnesium, this was exothermic. It gave off a ton of energy. So forming bonds is exothermic, breaking bonds is endothermic.